Just give me a minute. Can you see my screen? Yes, no, please.
Yes, sir.
Okay. What is this? Okay, so let's get started. Welcome back. So we have seen how to make two machines communicate the issues out there, then how to share a medium if more than one machine wants to communicate directly. And now we will start actually getting into networks as you see nowadays proper. And we start with kind of, so to say, smaller networks called local area networks or LAN. You have heard the term. And the definition of what a LAN is kind of changed a lot since the early times it was invented. So as I kind of told you, it's both little confusing but also a little fun if you start thinking about it. That this is where the things will start getting a little bit confusing. You will see things in the textbook and then I will come back and teach you those and then I say, no, but you see these are not used. Okay, but you need to kind of, both are important. It's important to know what are the things in the backend because they are still being used in other places. But then it's also important to know what is happening in the modern day LANs and so on. So I'll try my best to kind of give you a picture and you should also try to kind of filter it in your head. So let's get started and let us not confuse it too much at the beginning itself. Okay, so what is a LAN? I will point out again later on. In the old days, LAN used to have a very specific meaning. It's very hardware-oriented meaning. There was a wire to which everything was connected, and you say that this is my LAN. All these machines are the local area. You can see the local part of local area networks and so on. But broadly, what a definition of LAN is nowadays, and this will somewhat become clearer after we go through the next couple of hours. Okay, and I will come back and summarize at the end. Is seen as what is called a broadcast domain. See, the set of machines such that when I send a broadcast message from one machine, it will reach all other machines. So when I say, are these two machines in the same LAN? What I mean is basically, if I broadcast, and I will tell you again what is meant by broadcast. Okay, how do I say when the message is broadcast? Just give me some time. If I broadcast a message from one machine, does the other machine get it or not? Because not every machine is going to get it. Only the ones within the same network, so to say, same local area network will get it. So the definition of LAN nowadays is more in terms of the broadcast domain, saying that which all machines can hear each other's broadcast. And this will become clearer as we go on. Now that does not mean machines can only broadcast in LAN. Obviously, a machine can send. So if I think about a group of machines in a LAN, okay, we'll see that these machines will have addresses, identifiers, and then you can say you can send a message to one specific machine if you know its address. You can send to a group of machines. Okay, so you can either unicast messages sending to one specific machine, or you can what is called multicast messages sent to a group of machines. So you have basically three different types of communication usually: unicast, one-to-one, multicast, one to a group, or broadcast, which is one to all. But then definition of all varies as to what in context, what context you're talking broadcast about. Okay, and typical characteristics. Again, these are kind of, that's why I put the word usual. In the old days, it was always a small geographical area, a few kilometers max. Okay, that too will require repeaters and so on. But nowadays, you can have LANs, because again, the definition of LAN is something that is broadcast domain. You can have LAN spread over a larger geographical area. Just to give you an example, so IIT Kharagpur, we are at Kharagpur. it has an extension center in Kolkata. It has an extension center in Bhubaneswar. Okay. And the machines in Bhubaneswar, so there is a common LAN connecting machines in Kolkata, machines in Bhubaneswar, and some machines in Kharagpur. Okay, so the physical reach of that LAN is actually much larger. Okay, Kolkata, Bhubaneswar, and Kharagpur. But usually you will see it when people implement it in their own domains within some smaller geographical area, like within the campus and so on and so forth. Okay. Relatively high data rate, again, high is defined by what is your need and what is the context, but still relatively high data rate compared to what is this relativity? It is compared to basically your wide area network. That means if you think about the speed at the internet, it's probably going to be much larger than that. Okay, but again, that is context dependent. Okay, and this is the one that is kind of is still true. Okay, usually it will be under a single administrative management. This is very, very important. Okay. As I pointed out, if you think about the internet, when we discussed the layering and other things last time, the entire internet is not under any single administrative control. There are bodies that govern its different operations, which protocols go on internet, how our addresses came on, and we'll see some of them as we go on. Okay. But then if you look at all the machines, for example, okay, and the interconnection, the actual physical wires and so on, they are not all under the same management. IIT Kharagpur owns the IIT Kharagpur's machine. Then IIT Kharagpur uses RailTels as an ISP. So RailTel owns the RailTels routers and network connectivity. Then RailTel exchanges data with other people, there are other ISPs and so on. Okay. And as you know, many of you know probably that there are lots of links that go under sea also. These are called submarine links. Okay, so there are separate companies that operate only those links, and the other people take their services. So the internet is not under a single administrative management if you look at all the components, but a LAN will typically be under a single administrative management. Okay, but this relatively high data rate that we'll see LANs spreading around 100 Gbps also. Okay, so they're relatively high, but compared to the speed over wider area, like when you go across networks in the internet. But what is high, what is low will depend on the context. And they will usually again be spread over a smaller geographical area. Again, the small large is relative to the context. But just to give you an example, IIT Kharagpur campus, for example. So you have a LAN that's spread over the campus. So this Kolkata Bhubaneswar example that I gave you is kind of more a exception than the rule. Okay. What about how do I connect the machines? Okay. So this is at the beginning you had bus, star, ring. That is how LAN started. Okay. So you had topologies like a bus topology. So you have one line, basically one wire going, and then my machine is really, really slow to respond. Okay. And you have machines connected here. Okay, so this is what is called a bus topology. I don't know what is happening today. There are always surprises. Okay, star topology, as you know, is basically now all these end things will be your machines. I'm not sure what is happening. Okay, and a ring topology is a ring, as you know, basically. So this where, for example, ring has kind of become extinct as a LAN topology now. Star is there, bus is also kind of become extinct, but then we'll see that most of the LANs nowadays are what are called switched LANs. Okay, you have heard, you see network switches and so on. So we'll look at this thing later. And the specification, when you talk about a LAN, you specify the details of a LAN are mostly at the physical and data link layer. So if you recall, the physical layer was basically about the electrical details, the connector details, the type of transmission media used and so on. So the different LAN standards will specify different things for them. We'll just look at some simple things of that, but again, we don't go too much into the physical layer. And then you have the data link layer. If you recall the functionalities of the data link layer, anybody? What are the functionalities of the data link layer? Anyone?
The framing.
Okay, good. Framing and deframing. Anything else? So
detection.
Yeah, so technically good. So technically, when we talk about textbook functionalities of data link layer, remember the data link. Okay, this is what we did for the direct communication between two parties. So all the things that we talked about earlier. So framing, deframing, okay. Medium access control, sharing the medium if there's a shared medium, okay. Error detection, flow control, error control. Technically, all these things are part of the data link layer. Okay. So most of the specifications are this basically. So what are the physical layer details? What is a frame size? What is a frame format? Okay. What is the medium access control methodology? What is the error detection technique? Okay. So different LAN standards will specify these different things. Okay. So we will study Ethernet, which is the de facto standard protocol for LANs. So I am not aware of, there may be, but there used to be others, but now it is all like Ethernet LANs only. So the general issues about framing, okay, about medium access, how do you do CSMACD, all those things that you have already covered, error detection, flow control, error control. So we'll not talk in general about them. The similar things will be applied here. We'll basically study the details of Ethernet, which is the de facto standard protocol. And we'll immediately see things will become a little bit confusing. Okay, here's a bit of a history. Okay, I talked about it in the first class also. Developed in the early 70s in Xerox PERC by Metcalfe and Boggs. It's a very famous paper, 78. I've given you the reference also in the first set of slides. Okay. And then Xerox did nothing with it for some time. Then in the early 80s, this was picked up by the company Digital Equipment, which is no longer DEC, okay, as it is known, as it was known. It's no longer there. It's one of the biggest computer companies after IBM at that time. So DEC, Intel, and Xerox standardized the 10 Mbps Ethernet. Okay. You have to standardize because you cannot have, because when you're trying to talk about a network, as we have discussed, you cannot have one entity, one manufacturer doing everything, basically. So these proprietary networks were there. So for example, when IBM, if you were in those days, there's not too many, there are no PCs or nothing. So computers used to be brought only by large companies. So in a company, you have 10 computers and you want to connect it by network or something, okay, local area network. IBM had their own network. DEC had their own network, which have their own protocols, own standards, own hardware and everything. So you cannot really connect an IBM machine with a DEC machine. So all these things, Ethernet, then socket programming, the IP network, TCP/IP, etc., were an effort towards trying to make everything interoperable. Prepare a standard. So if DEC plays by the standard, IBM plays by the standard, everybody else plays by the standard, okay, then their machines can interoperate. Their network entities can interoperate. So I can have a switch from somebody, communicate with a switch from somebody else. Because the packets that you're sending out on the network have the same format, they're following the rules of timing and everything. Okay. So the formula is what is called the DICS standard, and which is, again, there was a couple of revisions, and the final one is called the Ethernet 2. Okay. So that was the one thing, Ethernet 2. And then IEEE took over. There's an IEEE working group, 802, which took over the work on Ethernet standardization and standardized various physical layer MAC combinations. As I said, there are different standards which basically specify different combinations of physical layer. So if you are using it over fiber or are you using it over copper, and then what would be the wavelength transmitted for fiber, what kind of fiber? I'll just give you some examples shortly. And then a single, what is called a logical link control on top of them. So these are just standard names. 802.2 was LLC, 802.3 was CSMSCD, one persistent CSMSCD. 2.4 was a type of LAN token ring which is non-existent. Okay, I'll have one slide up for it at the end, and many others. For example, all your wireless standards now are 802.11 something. It was originally 802.11 A, B, etc., etc. Now it is AC and beyond basically. So just one thing about this LLC CSMSCD business. So this LLC is the one that kind of LLC is the one which abstracted out basically this error control, flow control, all these things off the top. Basically, not error control, yeah, flow control and error control. So if you look at the standard OSI stack, okay, then basically data link layer is this entire thing, as I said, framing, deframing, access control, error detection, error control, flow control, everything. So this medium access control part, so physical layer part took care of everything. This framing and medium access control part is here. That was this 802.3 and all those things. And this logical link control part separated out the error control part and so on. Okay. So rather than specifying the entire thing as one standard, 802.2 and 2.3, 4, etc., basically says that this medium access will vary depending on what kind of medium you're using and so on and so forth. Okay. But then on top of that, assuming that you have grabbed hold of a medium and you're communicating, how you do flow control, error control, etc., will be a single entity, 802. Okay. Forget this LSAP thing and so on. Now comes the confusion. Okay. So specifications are both data link and physical, but Ethernet 2 specifies only the MAC sublayer and physical layer. So that means Ethernet 2 does not do any error control, flow control. It does framing, deframing, it does medium access, it does error detection. Okay. And Ethernet 2 is the de facto standard thing used in TCP/IP layers, which means TCP/IP layer, when you have a TCP/IP stack, at the data link layer where you use Ethernet 2, there is no error control, no flow control. So this is where you have to kind of, keep both perspectives in mind. When we talked about data link layer, and if you look at the textbook definition of what is the functionalities of a data link layer, it is everything. How do you make reliable communication over one link? Okay? And that will include everything. Medium access control, error detection, error control, flow control. So that's the textbook definition of the functionality of data link layer. But then what exists today, mostly, okay, the entire TCP/IP stack uses Ethernet 2, which means they say, I'm going to do framing, deframing, medium access control, and error detection. But if I detect an error, I will not try to control it. I will just drop it. I'll link this up again when we do IP/TCP and so on. Okay. So why do you think so? Why did TCP/IP is the de facto standard? Data link layer says error control. Take for example error control. Okay. Why do you think? You may not be able to answer it, but I still want you to start thinking. We are a little bit ahead of the other section, so we can afford a little bit of time. Why would not I want to make my link? So here is what Ethernet 2 will do. You'll get that CRC check. If it finds the frame is in error, you'll just drop it. Do nothing else. There is no stop and wait, no go back in, no selective reject, nothing. Why do you think so? Why does not it try to do error control? Any idea? So you may not be able to answer it right now. Okay. But you see, basically, your network is going to be multiple links. Okay. Now, what this data link layer is doing, is just making one of those links, two entities here and here, okay, make them communicate reliably. But this, I have no clue what is happening. Anyway, but this thing in the middle, these round things, okay, are going to be your routers, and we can see later on that their packets can be dropped in the routers also, even if they have reached correctly. So even if there is no bit error or nothing, your frame is perfect, then packets can be dropped at the router. We'll see the reasons for that. So if I look at end to end, okay, the point is that even if I make the links perfect, okay, there is always a possibility that what is connecting those links, the routers in the middle, okay, they may drop the packet. So I may have to do end-to-end error control anyway if I want reliability. So what TCP/IP did was basically saying keep the Ethernet layer very simple, okay, don't do all these things, because even if I do this, I may still lose packets at something else. So if you want reliable service, push up the functionality up. It's up to you whether you want reliable or not. And that's what it did when it did TCP and UDP that you are doing in the lab. It says if you want reliable, I will give you error control at the TCP layer. And all those things that we have seen will be done by TCP layer. If you don't want UDP. But by default, I will not give you anything always, because first of all, you may not want it, okay, at the lower layer. And the second thing is that even if I make at the lower layer this links reliable, okay, over between what is connecting those two links, there can be drops in those routers also. So there is no point, you know, doing it partially there and spend the time, because everything takes time. If you try to kind of improve your data transmission speed, your throughput, you'll have to reduce the time at the layers, basically. As opposed to that, if you work with IEEE, then you will use one of the IEEE 802.0 lower layer MAC things for the data link and physical layer specification, and then you will use 802.2 on top of that, basically. All right. Not many people use 802.2 plus this nowadays. Okay. For the reasons that I said, most implementations that you will see is Ethernet 2 implementations, but it is there. So this was the, if I look at just 802.3, which is just CSMS, you don't have to remember all this, okay, but try to get a feel of this thing. Okay, so you can talk intelligently with people. We are not going to ask you in the exam 1000 base LX, what is the medium type for that, okay? You don't have to know how many of 1000 base things or so on, but you need to understand what is this meaning of 100 base, what is this something's coming from. So IEEE 802.3 is a working group for dealing with LANs, specifically with CSMSCD, okay? And within CSMSCD, everything that is using CSMSCD, okay, you have a collection of standards, okay, that defines various combinations of Ethernet types and related issues. So here are some examples. So first thing, so this 10, 100, 1000 at the beginning, or 10G, etc., is basically saying what is the data rate. Okay. So unless it is G, it is in Mbps. So 10 base, all those things will be 10 Mbps. 100 base, all those things will be 100 Mbps. 1000 base, all those things will be 1000 Mbps. 10G is 10,000 Mbps, basically 10 gigabits. Base stands for baseband. Okay, it's a baseband signal, meaning basically its frequency bandwidth range will be from 0 to something. So at the lower end, it's going to be 0. Okay, not very important for you. And this TEF, TX, FX, LX, etc., 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 these kind of identify the media and something else. Okay, and associated physical parameters. So T usually, when you see a T somewhere, it's all twisted pair. So the T comes from the twisted pair UTP. Okay. So if I'm using a 100 base TX, which says basically it's a 100 Mbps LAN, okay, and the connector, the medium that I will use with it is UTP. There are further divisions. I'm just giving a very high level view out here. For example, if you use 1000 base T and so on, okay, you cannot use a Cat3 cable or something. So you have certain other specification of at least minimum what kind of UTP cable and so on. Okay, but those aside, if you see a T in there, it is basically twisted pair. That means the medium is twisted pair, so the connector is what is called the RJ45 connector. So I'll talk a little bit more afterwards on that. Okay. And then you have this FX is fiber, LX is also fiber. Okay, but then different. SR stands for short range. So SR will have multi-mode fiber and so on and so forth. Okay. You don't have to remember this, but so this is what basically, so each of them will have basically is a standard basically, which says, so if it's 1000 base LX, it exactly specifies what is the data rate, what kind of connector, what kind of transmission media, what kind of signal that goes, what kind of encoding, all those things that we have seen at the lower end. So what kind of medium access control, everything is specified. All the timings, everything. Okay. Okay. So all of them, as I said, in the same basic frame format. And the difference is mostly in MAC and physical layer details. Again, mostly like parameter values, they're all CSMA-CDs. Okay. Encodings, media, connector, as I just mentioned. Okay. And here comes the second bit of confusion. So you have heard about CSMA-CD. Everybody will expect you to know CSMA-CD, ask you questions. Okay. But if you look at modern day LANs, they're all switched LANs with full duplex operation. And we'll see CSMA-CD is not needed. Right? Mostly it's not needed. Okay. So this becomes a little bit confusing. So I will talk about it once we do some more of this thing. So within the next class, basically. Okay. So the idea is the CSMA-CD was meant for, as you have seen, shared media. Okay. And the shared media in which, so if you have in the old days shared media, if you had a media like this, okay, and there are machines. And you have other machines connected out there. It's half duplex, obviously, because if anyone is communicating, okay, in one direction, if you just take two machines, okay, if this one machine is connecting to the other, communicating with the other cannot communicate because they are using the same media. Okay, the collision will happen if both of them try to communicate. So CSMA-CD was meant for originally for half duplex operation over a shared media. Okay, we'll see basically with switched LANs. Okay, this notion of shared media is kind of mostly disappears and something else happens. So we'll wait for some time. We'll discuss that. But all I'm trying to point out is in your mind is not something that you can just read the textbooks and answer in the exam and you learn basically. You need to think a little bit, get confused, ask me questions, and we'll discuss it. What is the relation between the standards? As I said, TCP/IP uses Ethernet 2. Okay. Both types can coexist on the same LAN. So it is possible for an 802.3, a machine that is using 802.2 and 802.3, okay, communicate with an Ethernet frame. Okay, how is that possible? We'll see later on. But remember, this brings down a very, very important issue that we are trying to give a little bit of hint in your assignment 3 in the lab also. Okay, that a network is going to be a collection of devices, protocols, everything from different people. That's why there has to be agreement. Okay, and it has to be interoperable. In a large network, okay, if you bring in something new, you cannot just say, I got this great new protocol, hey, tomorrow everybody must start using it. You cannot do that because everybody is, first of all, not under your control necessarily. And then even if you is in control, suppose you have a LAN, you may not be, kind of for cost reasons, other reasons, you may not be able to change your LAN overnight to something else. You may today want to, upgrade 5 machines because they require new hardware. Then tomorrow you have some more money, upgrade 5 machines. So there is always going to be some time in which things of the old and the new have to be there. Okay, things that are running different things, and you have to worry when you design the protocols, design the system, that they should interoperate. You cannot suddenly one day say that I have this great thing, I'm going to install it on a machine, on my server. So you see, all clients must change yourself or nothing will work. You cannot do that. Okay, so this was very old, but then Ethernet 2 was there, IEEE 802.2.3 is there. Their frame formats will see a slightly different. Okay, But we'll see there is a way to interoperate it. We figured out a way to interoperate it. That means a machine that is sending Ethernet to frames, okay, the other side, even if its protocol stack is 802.2 and 802.3, can still understand that it's Ethernet to frame and act accordingly, and same the vice versa. So we'll see how that happens little later. Okay. This is the other thing, the minimum frame size. We discussed this. Okay? That if you want to use CSMA-CD, a frame must take more than 2 tau time to send. Tau is the max 1 way propagation delay to detect collision. We discussed this during CSMA-CD, right? Yes, no? Why the frame size has to be minimum that? I think we did that in CSMA-CD, right?
Yes, sir.
Yes, right? Okay. Yeah, I think so. So the 2D R by V thing basically. So this first part, the example scenario, we have already discussed in CSMA-CD. Now, this minimum frame size for 10 Mbps Ethernet is 64 bytes. Okay. Why is this 64 bytes? It's more historical. Okay. So the first thing was 10 base 5. So 10 Mbps and the 5 came from that one segment. Okay. That means something that you can transmit without a repeater can be 500 meters. Okay. So basically the maximum distance that D for first set of lands was 2.5 kilometers, but with repeaters in between. Okay. So it was like okay, one more. So it says that the maximum distance between two end machines cannot be more than 2.5 kilometers. Okay, you don't need to remember this, but just a historical why this 64 came in. Okay, and then each segment that is between something that does not see each of these 4 things in the middle are repeaters because the signal did not have enough strength to go from here the end to end without being amplified. So you put repeaters, and as we have noted, repeaters will be in this race basically, you cannot have more than this large number of them because the delay will increase. Okay, so you had 500 meter each of those links, 4 repeaters in between. That's the max allowed by the standard. That is 2500 meters. So your propagation delay of 2500 plus 2500 plus the repeater delays which were taken to be 2-3 microsecond. Okay. No clue why this has become this sensitive. Anyway, so that came out to be around 45, 49 microsecond. So you wanted to basically at 10 Mbps transmit enough number of bits that will take more than that time. Okay, and the slot time, which is the time to transmit the minimum size frame, came out to be 512 bits. 512 was just again to round it off to a nice power of 2 base 10. Okay, 10 Mbps, 51.2 microsecond. So that's where the 64 bytes came from. Okay. So if so not one thing, based on your knowledge about CSMA-CD, if a station transmits for 1 slot time and does not detect any collision, okay, that means it will be able to finish its transmission. Because 1 slot time is the time for its signal to go to everybody, because that's the maximum length. And if anybody has sent any jamming signal, the jamming signal to come back. If you are still transmitting, after 1 slot time that you will be able to finish your transmission, nobody else will. Because if anybody else was trying to transmit and detected a collision, the jamming signal would have come back to you by now. Okay. Are you with me? Yes, no? Yes or no? कोई तो कुछ बोलो यार. Can you hear me?
Yes, sir.
Yeah, did you understand? Again, forget about this 64 bytes came from because you calculated the end-to-end delay and all these repeated delays and so on. So that's a detail that you don't need to remember. So you wanted that came to 45, 49 to something at 10 Mbps should take more than that. And then you round it off because 51.2 microsecond, 512 bits, same lines. Then what is this 512 bit? That means the minimum frame size, which means that if you transmit at least 512 bits, okay, 64 bytes, that means after you have started transmitting, okay, and then after one slot time, within one slot time, that means 64 byte transmission time, everybody would have heard it along this thing, okay, and if anybody has detected collision, the jamming signal sent by it would have come back to you. So you may have a 1000 byte frame. 64 is just the minimum, doesn't mean that all your frames are 64 bytes. Okay? But what it is saying is basically that if you have been able to transmit for at least this long, then you know the remaining, say you are transmitting 1000 bytes, so remaining 936 bytes, you will definitely be able to transmit because nobody else will be getting the carrier free now. When they do the carrier sense, they will see your signal. Collision occurs only when two nodes detect the carrier to be free at the same time. Okay, not at the same time, before one's transmission is restarted. But with one slot time transmission over, you know that everybody must have heard your thing and nobody has complained, so nobody has detected a collision. So you can now safely finish the rest of your frame. After one frame is over, it is back to CSMS sensing the carrier. Is it clear?
Yes, sir.
Yes, okay. But then what happens for 100 Mbps, for example? Because now your things will be pumped out. Remember, what is this Mbps? It is the data. What does that mean? It is the rate at which you are putting bits on the wire. Okay, how fast can your transmitter pump out the bits on the wire? So with 100 Mbps, it's pumping out 10 times faster. Okay. So if you were to design, okay, to maintain this same thing that the collision has to be detected, what are your options? See, I cannot keep it at 51.2 microsecond. And therefore 6,000. Okay. Not that I cannot, okay, but I am asking you. Remember that formula 2D R by V. Now your R has become 10-fold than R. So your minimum frame size was 2D R by V. Okay. So R has become 10-fold. So your minimum frame size should become 10-fold also, 640 bytes. Do you agree? Okay, I have no chance of engaging anyway. So what 100 Mbps did was, we'll talk about it later again, was not to change the minimum frame size. So minimum frame size is 64 bytes. Stay. Okay. But that means that your slot time has to go down by 10. Okay. Your round trip delay has to go down. If your round trip delay has to go down, okay. So 64 bytes, if you keep it, then your slot time becomes 5.1 microsecond. Because you can pump out 64 bytes, it's not 10 Mbps anymore, it's divided by 100 Mbps here. Okay. So your slot time becomes, what is this? So your slot time becomes 5 microseconds. Okay. So this entire round trip thing must come back to you within 5 microseconds. So your only option was to reduce the length of the maximum length. So you can no longer have this each segment length to be 500 meters and so on and so forth. So you reduce the fast Ethernet. Then we'll see what it is shortly. Gigabit Ethernet. Again, you can do the same trick. Okay. But then, we'll see what happens out there. But My point is try to understand the problem. 64 bytes is very classic network basically. 64 bytes was based on something on 10 Mbps LAN long ago. Okay. Now, when you go to 100 Mbps, you have to maintain compatibility with the 10 Mbps because there will be devices which are still operating at 10 Mbps. You may have a faster device with 100 Mbps, but there may be devices which operate at 10 Mbps. So how do you make things interoperate? Okay, but at the same time, make sure that there is a minimum frame size for 100 Mbps also. So the collisions are predicted for 100 Mbps also. So just remember the problem. We'll come back to it. So here is the Ethernet frame format. So any Ethernet packet that goes out has to follow this frame format. Okay, look at the bottom one first, the Ethernet one. Okay, so there is a preamble. Okay, we have seen that in the frame. There is a preamble. This is a sequence of bits, enough transitions to synchronize your clock, also to detect that something has happened. So basically, your line will be in some idle state. Idle state will also have to be defined, and then there will be your receiver will be kind of listening in for these bits, and it starts seeing these bits happening. It listens for some more time, which is basically 8 bytes. So all those 8, 6, 6, 2 are in bytes. So it says 8 bytes of the pattern that it expects. It knows it is the start of the frame. That's how it detects the beginning of the frame. Okay. Then comes 2 6-byte addresses. Okay. This basically says for which device it is and what is the source. So it's a destination address. It's called the destination MAC address and the source MAC address. Who is sending this frame and for whom is it meant? Okay. Then forget, so we're looking at the Ethernet things. There's a type field. So this will have some values which says, basically we have seen during layering, okay, we'll come back to this again when we do IP and other things, that all higher layer protocols are getting encapsulated in the Ethernet frame. Okay. So think about basically that you have an IP and you have some other protocol. So both their frames, or both their data got encapsulated in the Ethernet frame. So I got some IP data from top, okay, and basically what I did was I took this data, okay, and I put a Ethernet header on top of this. So this is my Ethernet header. This is the data part of the Ethernet. Now, when the packet goes to the other side, okay, how does the receiver know which protocol, which higher layer protocol should process this data? It's like, think of this as function calls. I'm in a function that is checking this packet, this frame rather, okay, and I want to call the appropriate IP process, ARP process, whatever. I want to call the appropriate function. It's an IP packet, I'll give it to the IP software. It's an ARP packet, I'll give it to the ARP software. So IP, ARP are just names to you now. But the point is, all the higher layer network layer protocols, all their data, whoever one sends in, is going to be encapsulated in Ethernet frame. So at the receiver side, when it comes, if the IP is sending it, it should go to the IP software there. So now the receiver has to know which software on the sender side has sent. Whose data is it carrying? Is it IP's data? Is it ARP's data? So the type field tells it this. So again, there are standard values. So IP will have a specific value, ARP will have a specific value, and so on. So it looks at the type field, knows, okay, it's the IP's packet. So it'll just call the IP software. Okay. And then this FCS 4 bytes at the end is the frame check sequence. This is the CRC check that we have discussed. And this middle thing is data plus pad. Okay. So if you look at this, you have 8 plus 6 plus 6, that is 14 plus 6, 20, 22, 26. Okay. 26. Yes. 26 bytes basically. Okay. And the remaining thing is the data. Now I want a minimum size data. Okay. So this has to be minimum of 46, maximum of 1500. The maximum is there just so that nobody hogs the channel for too long. Okay. So there's a maximum frame size also. But what if the frames, somebody wants to send 10 bytes of data? That is less than the minimum size. Okay. So what happened there? If it is less than the minimum size, what happens? You have to send packets with at least this much data. Because if an Ethernet frame comes with less than 64 bytes of size, okay, it's going to be dropped. It's called runt frames. Okay, it's going to be dropped. So you pad zeros basically. So this is all zeros. You pad zeros if the data is too small to make it basically of the same size. Are you with me?
Yes.
So any Ethernet frame that goes out on the wire will have this thing. IEEE 802.3 will come to that. You see, there's a instead of type, there's a length field, okay, which contains the length of the data, and then this LLC PDU pad is similar because you want to make it the minimum size. So if your data size is less than the minimum size thing, you're going to pad zeros with it, okay. Otherwise, this LLC PDU thing we'll look at later, okay. But this type and length field are the main difference out there. Okay. So let's end with something. Okay. So now try to visualize basically with me a bit. So suppose there is a frame is being sent on the shared media by one node. It has got there is no collision or anything. Just suppose it has got the media property. Okay. So there are 10 machines of name 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are their addresses. So let's say machine 1 sends a frame for machine 9. Okay. So what will happen? There will be a preamble, which is this pattern for 64 bits, 8 bytes. Destination is 9, so 9 will be here. We'll see this form different format, but just 9. Source is 1, so 1 will be here. The source will know which higher layer protocol has given it the data. Let's say it's IP, so IP's code will be here. Okay. Then this data will contain the data, the data that the higher layer has given it. If it is more than 46 or higher, then it is fine. Otherwise, I'll pad zeros with it. Then on this entire thing, without the preamble, I'll compute the FCS. This is CRC. So DASA type data pad. And I'll put the FCS out there. Okay. Now, when this frame is sent on the wire, everybody gets it because it's a shared media. So one sent it for 9, but 2, 3, 4, 5, 6, 7, 8, everybody will get it because the physical layer is a receiving signal. It does not know anything about who is it for or something. So all the machine's physical layers will get that signal. So it will pass it on to the data link layer. Data link layer will form the, so all machine, think of machine 3. It will also get the frame, deframe it, find out, oh, this is my frame. It gets the preamble, knows beginning of frame, it gets the entire thing. But then it will first do an FCS check. If the FCS check fails, it drops the packet because the packet is not proper anyway. Then machine 3 looks at the destination address. It sees that the destination is 9, not 3. So it will not further process the packet, drop it. It knows it's not further. So everybody will get it. All of them other than 9 will drop it. Only machine 9 will see, oh, destination address is 9, that is me. Okay. Then it will look at the type field, say, oh, it's IP, take out the data, and then call the IP software, whatever the function that will process the IP packet with that data out there. But the point is that it will reach the data link layer of every machine on the shared media. As of whatever we know about CSMA/CD at the shared media. Are you with me? Yes, no?
Yes, sir.
Okay. But then, how do I know the sender has supposed padded something? How does the receiver knows which part is data and which part is pad? Now for IEEE 802.3 frame, that is easy because you have the length field out here. Okay. It tells you exactly how much the data length is. So if you get, let's say, 46 bytes and you have only 10 bytes of data, length will be 10 bytes. So you know that 10 bytes of data, remaining 36 bytes are pad. But what about here? There is no such length. Again, it's a question you probably will not be able to answer now. But I want you to kind of see the thing that I'm pointing out is you can mark the frame format. Okay, you need to remember it, at least for exams and all right now. Okay, but then you also think about this question that try to visualize the flow of the packet. We'll do it more and more as we go higher layers. Okay, so somebody sent a frame. What is happening to this? What does it put in each of those fields? Okay, who will receive it? How will they process it? And if you try doing that, you will immediately see the problem that this type field just is some protocol. Nowhere in this frame, okay, is any data which helps the receiver in deciding if it gets a 46 byte frame, 46 byte data here, okay, whether this is padded or you had exactly 46 bytes of data. Which part is bad? You could have 00000 also as data. Your entire data may have been all zeros, 46 bytes of that. At least get the question. That's what I'm saying. There is another major question that nobody is asking. Okay. Again, try to visualize and you will again get this question. So there is a preamble to detect the end of the frame. Now this PDU size, the data size is variable. Moment you have variable data, you need to start asking yourself question. In the lab also you do the same thing. Okay. How do I detect the end of the data? So here the question is, how do I detect the end of the frame? There is nothing. In our generic frame structure, there was something to detect, say that, end of frame delimiter or something. There is nothing here in the frame format of Ethernet, at least what we have seen so far. Okay. So I leave you with two questions. How do I know the pad, distinguish the data from the pad in an Ethernet 2 frame? It's a question you probably will not be able to answer right now. And the other question is, how does the receiver detect the end of the frame? Where does one frame end? Because the data size is variable. All you're getting is 0-1 bit space. There's nothing, there are no lines drawn out there to say this is the FCS start of the FCS something. You can have 46 bytes, you can have 100 bytes, you can have 200 bytes. So how do you know, basically? Okay. So think about them. We are out of time today. We'll come back and try to finish it tomorrow. Any questions? Let me turn off the recording. Okay, so if there are no questions, class is dismissed. And I will see you in the lab.